by talking about RNN's use for in pediatrics. He talked about this paper about entity embeddings. I'll put that in here too. The taxi prediction. And was there a paper for that one? I don't remember.
Yes.
I think so.
Do you remember where in the lecture that was? Is that towards the middle?
I would go to the end. I would say even, was it after the theory too?
I think it was before.
Okay.
Okay.
Yeah,
Sure where that
I
was.
think it was that.
This one? The
Yeah, the point where you posed the architecture.
I'm trying to find out. Oh, right. Artificial neural networks. Okay, let's go get that. Artificial neural networks applied to taxi. This one. You can get that one down too. Right, I do remember he said something about this. Okay, so why don't we start? Is there any particular of these these 5 papers that we want to look through? Maybe we'll do it in the order that was discussed. Shall we do it that way? So you first started talking about this Recurrent Network paper where they took data scientists into the hospital and on the rounds that doctors were doing. And they came up with RNN to predict mortality. And so he said it's a very simple structure, right? Just the same ones that we know about, where they have certain types of data being put in, just normal sensor reading data, and I think he also said that one important thing of this was that, oops, I skipped it somewhere. That the database signals are sparse. They're irregularly sampled. Like you won't have labs all the time, right? You have labs only at certain points, and the sensors might come off, and you might not have vitals measured at certain times. So all of this matrix is sort of not fully developed. So instead of imputing information, what they do is they just add a delta t into the measurement, right? So you're feeding that into the inputs, and then the RNN is predicting the mortality at time t, and then some information describing that. So
we don't have any signal for the t plus delta t point, data point. That's the point?
No, I think you do. It's just that some of these labs may not have, or some of these informations may not be measured at certain times. So then when you input the information, you just tell when is the delta t since the last time it was measured.
Oh, okay.
Something of that sort. That's what I understood from what Jeremy said, but I'm not 100% sure about that. Shall we go to that part?
How is it very different from regression?
From what?
Regression, you should in a standard regression model, you have for every time step you can measure almost everything, right? Like this is way sparser because you might get for every time step you might get the heartbeat because that's easily to measure, but you only like once a day you get the lab report. So like if you want to predict at 5 in the morning something, you say okay, the lab report is already 12 hours long, 12 hours old. Whereas at this point you still have like a up-to-date heartbeat. So basically for each dimension you say okay, this information is so old, but you still want to be able at every time point to make a prediction. It would be really weird only to be able, okay, right after the lab report, now I'm ready to make a prediction again. For the next 12 hours, please don't ask me because I need a lab report.
Yeah,
Right.
I understand the motivation. I'm just trying to understand the technical side of things.
Ah, okay,
Yeah.
sorry.
Right. So you can do imputation, right?
Right. That's when we have missing data, that's what we do standard data mining.
Sometimes we do that, right? Sometimes we will just specifically say, okay, it's missing, and then we don't use that measurement.
Right.
But oftentimes you do imputation to fill in values that are not there, right?
Right.
Yeah.
Here, instead of doing that, we just ask the network we ask the network to impute while it is learning the time series. Okay.
I'm not sure whether they do that. They say here, okay, if a psychologic or laboratory variable had no recorded value, then that variable was set to 0 at all time points for that encounter, right?
Would imputation, like standard imputation, give the network or your regression model the impression that this data is as important, like as good as non-imputated data?
Mm-hmm. No, I don't know.
I have a question. So if you do is imputation something you do outside the network, or is it basically does the network know that you did imputation? Because that kind of
if you impute and feed into the network is agnostic to the imputation.
Okay, but
it won't know.
It shouldn't be, right?
It should.
It shouldn't be
better if it's not. So I think that is the point of it.
Right. So what Jeremy said is instead of doing imputation, I think what these folks did is they let the network know that there are 0 values there, right? Yeah. By giving this delta t information that says I didn't actually have a measurement at this point in time, right? But the next time I get a measurement, I tell you that, hey, this is an actual measurement, and the last time I measured this variable was delta t ago, right? So they're feeding that information into the RNN. So the RNN is not just getting the actual signal information at time t, it's also getting this the last delta t that particular signal component was being measured, right? And then the output was the regressive value y for how long, how likely that patient is to make it or not.
Right. It is regression basically, but they're doing regression in a fancy way.
It's also I'm not sure how much that comes out in the paper. He shortly mentioned that the data has also this feature that usually when something goes wrong, like you have jumps in your measurements. So like if you have organ failure, you have like spikes and something like you can clearly see, okay,
something is going wrong.
Something is going on. Your heart rate jumps from the normal one to like something really high.
Right.
How does the regression handle those?
This
is always a challenge in regression.
Yeah, I have no idea. He just mentioned that in like 2 sentences that they also kind of have this feature. I'm not sure if they deal with this feature.
I don't think they need to deal with it specifically. I think it comes out of the measurements coming here, right? So when you get input at time, whatever, at this point in time and you get this point in time, right, there'll be a very vast difference in measurement. And then the RNN should be inferring that because of the change in the amount, and there's a very high likelihood that the mortality rate has changed.
But isn't that too late?
Yeah.
Isn't that when wouldn't you like to be able to know it before? Like if the spikes go up, everybody can tell you that something is wrong. Wouldn't you like to be able to say like 10 minutes before it spikes that
sure,
a spike is going to happen?
Sure. I don't think that this model does that per se. From what I understand, it's just giving you a prediction at this time period when I have these vitals, right? I'm making a prediction at whether you're going to live or not from the time period of now to delta t. That means the time period in the future, right? Until the next set of readings are coming. Right, then I make a new updated prediction at time, that new time t plus 1, whatever, right, where my delta is just between these 2 points. That's how I understood the paper. So I think you're very much right. If the signals, everything is normal here, and then suddenly there's a big spike here, then the neural network will say, okay, well, looks like you're not going to make it or whatever, and it's a bit late, right? But for whatever reason, that's still a very valid task, and they show some cases of that. I don't know what they said. So they have a couple different baselines. This PAIM2 and PRISM3, which does some predictions. But yeah, for their RNN, they basically have a stacked version, right? So they have at least 2 layers of three layers. It looks like, right? No, this is output. So that's the output.
So they specify some motivation for masking.
I'm not sure what they mean by masking. Yeah, let's see.
So, yeah, masking means it's not zero padding. It's you can mask by some other particular specific mask that you want.
Okay.
It's not same as zero padding.
Yeah, but I know zero padding. Okay, so no, not in machine learning. I know, but I know padding from pictures, but that's
No,
different
it's
data.
not
So,
what they're doing here.
so where do you pad
So,
here?
normally, so in text we have varying lengths of inputs. It's very common.
Yeah, okay, yeah.
So you pad the input with zeros, and then the RNN has to be told that you need to ignore those zeros. They are not actual signals. And that's called masking with zero padding and masking in that context. But a masking layer is different from that. A masking layer is like a gate. You have a particular signature or sequence. You can mask your output from the RNN to the masking, and then you can get a filtered output.
Okay. So it's something you do before the output or before the input? Or
After LSD.
after.
Okay, so let's see. I'm not really sure whether what they mean by masking is like that. So I think what they are doing, because they don't actually mention it.
The architecture again?
Yeah. Let's see here. No, this one, right?
Because the mask input.
Yeah, so input is, so every layer has an input and output. So and that's just the shape. What they're specifying is the shape, not the actual input.
So I'm not sure what they mean by masking. Did they say? How far into the future? No. So masking in the sense of dealing with medical information could be masking the patient's identity. So for example, they take the person's name and they scramble it to a string or something of that sort.
Because the network has to know what this is.
Yeah, so I'm not sure whether that is what is in here.
Anyway, so if they don't mention it, then it's not
say.
very critical. So we can assume that.
Interesting that they put it into the
So
graph.
where was this published?
It's an archive paper. I don't know what it was published. Yeah, they took anonymized EMR data, but I don't know whether they said anything about whether they masked it before, whether they had the real information before it was anonymized, and that was part of their layer architecture. So it doesn't say, at least I can't read it here. Yeah, so unfortunately it doesn't say very much. Okay. So do we want to discuss this paper in more detail? It doesn't seem like it has a lot of information on what it did.
They are specifying some calculus why it is, so I assume that it's not the standard thing that they are doing.
Sorry?
LSTMs. Somewhere down below.
Okay.
I saw some calculus going on. Yeah. So is it the standard thing?
I think so. I don't think it's very different.
Right, okay.
Yeah, because I think this is meant for, you know,
the
pediatrics side.
That's
they may not be very clear about all the ideas of doing this.
They're starting from the scratch, okay.
Yeah, so they're telling you, okay, I get information at T, and then I'm measuring the delta T between when measurements are put in, and then that's given to the neural network. The neural network is doing a form of a regression that's sensitive to time because I have information going between time as an RNN does, right?
I also had the feeling that Jeremy mentioned this paper not so much for the technical contribution, but more because like the hospital is really special in the sense that they have like data scientists which actually are working together with the doctors. So probably like the way they collect data and all this is way better than in a normal setting where you just have, oh, we have this database of our hospital from 10 years ago, which doctors randomly collected, and here they have like kind of a structured way to collect the data and to pre-process it and all of this. So they get workable results, I guess.
Right. Yeah, I think the point that Jeremy was saying that even something as specialized as a hospital, or they have prediction models that are very specialized and use expert input, gets beaten by a neural network by quite a wide margin here. You can see this is the what area on the curve, ROC curve for them, and then the RNN is doing fine.
What is PIM?
PIM, I'm not sure. It's their baseline prediction system. So these two are mentioned all in the same breath all the time. So I think these are the two models that are quite standard. Yeah, quite standard to compare against. Yeah.
Can you Google them?
Sure.
Like I feel like the person might heard before, but maybe just a nice.
Okay, well there it is. Pediatric risk of mortality.
Right. Okay.
It was
Something
developed.
measured.
It was it's a metric developed by some set of pediatricians using certain types of inputs, right? So I guess we could look at this in more detail if you wanted to.
No, it's okay. Yeah.
Medical papers are terrible to read.
Okay. Well,
Taxi destination prediction. Let's see that. Is it from Uber?
so yeah, okay, we finished this one. Let's go to the taxi one. This was the FAIR group again. Yeah, they did this prediction task. It was a Kaggle competition as well as a ECML prediction, and they were given information, right? GPS coordinates, taxi ID, beginning of the ride, right? And I think, did Jeremy say that he was looking at the third winner of this competition? No, that was for Kate, the Rossman. Yeah.
I think they won.
Yeah, they won by a big margin.
They won by a big margin, even though they didn't train their model to the end because they didn't have enough time, and then they trained the model a bit better, and then it got but I think here he was fascinated by the simplicity of the model.
Yeah, they just took the first 5 and last 5 destination data.
Yeah, so for the GPS. So the thing is, the prediction work. You got the string of GPS, then it was cut off at a random point, and then you should decide where they are going.
Yeah.
And what they did is from the available data, from the available GPS point, they only looked at the first 5 and the last 5. So to always have 10 data points. Otherwise, you would have like went down.
Very good. Yeah. This is a good idea. I mean, it's this kind of thing is not specific to. I mean, I've seen this kind of things since 2012. This is a typical way in which Kaggle competition data should be handled.
Yeah.
In our coursework also, in my master's, we did several projects like this. We always do some kind of trick like this, and it will work. It's always throwing away a lot of data when you have numerical data like this. And metadata is often more useful than the actual data.
And the second trick they had was the one with the clusters. So they basically decided beforehand which are points people go to often, and then made a softmax which kind of decided which of these points to pick.
The destinations, possible destinations.
Yeah, for softmax over possible destination, and the softmax also kind of gave you the possibility, if you're not sure between 2 points, you could have said, okay, they end up in the middle of these 2 points.
Oh, okay. We could take an average of those.
Yeah, we would just take the average of these 2 points.
So this is this part, right? You have all of these M similarity values with softmax. This is right where you're talking about candidate destinations, right? Instead of looking at plotting the exact coordinate, you're saying I cluster a bunch of coordinates where people typically go to, consider that as one destination, right? And I just take the centroid of that value as the place to go. So I have a fixed number of destinations that people go to, and I use that as the output.
It should only do like half. Maybe I have a wrong impression. I would say, okay, half the time you go to like the airport or the cinema or like the mall, but the other time you go home, and that should be like
a very big sparse cloud, right? Yeah.
It works. But probably the times you go home, like somebody starting from the airport or somebody starting from a mall, you are lost anyway.
Yeah, so it might be good to try to develop that type of model where you say, okay, there's a very large head of destinations that are fixed, right, from a certain small number of places you can go, and there's you know, a fairly long tail of you know, destinations that are specific to an individual, right? And I don't think they handled that right.
Mention it that they won even so they haven't. Again, I don't think he said that for any like technical accomplishments. It was like, okay, they used these 2 tricks and it worked well.
Yeah.
The flavor of the entire lecture was around like, look at these papers, they're kind of interesting. None of them has like one technical breakthrough.
Yeah, I think he's saying that a lot, that when you do problems in industry, there are tricks that you can do that are not scientifically perhaps very valid, but nevertheless get you a lot of mileage, right? So I guess in this paper we can say for certain problems, if there's a head of the distribution that might be more like a categorical thing, like, you know, you go to the airport or you go to the mall, then doing a clustering of that and observing data there would be very useful, right? And I think that appears in a lot of problems. I mean, if you develop personas for consumptions of certain types of data, then it can give you a good predictive value for certain things. Like, for example, if you have young children, what you buy on e-commerce sites is probably going to be very different than before you had children, right? And if you have a parent who's ill, again, the way you consume things are going to be very different than if you didn't have that. So if you look for those types of dichotomies in your data, you develop an algorithm or a clustered approach to different parts of your data set that might be better. That goes on to this other paper that he cited as being really interesting because it's not rocket science but does very well, which is to do embeddings, right? And we had talked about this before, where you take any type of discrete variable and you embed it, right? You make an embedding out of it so that you can do better with the semantics of this. And he talked a lot about dates, right? I think he's gone through this a number of times, that in the Rossman case, he said, especially store renovations. I think he made a case of that, where right before the store renovates, and you can sort of detect this because in the sales, there's all zeros, right? The stores are closed. Right before the store closes, they typically have some like going on the renovation sale, so there's a big uptick in sales. And right when the store reopens, there's a opening for business sale, and then there's a very big uptick there. There's a lot of models that don't take those types of things into account, like doesn't have the last delta t from the last zero sale. They'll make incorrect predictions, right? There was another couple of pointers that he said about time.
Yeah, he I also said, okay, the time to the next holiday, the time from the he took a date and split it up in like any possible way. Is it a holiday? Is it a holiday somewhere else? Blah blah blah. So all these things, your Google Calendar that tells you about your day, basically. And like he also made a big point about that you should even though a neural network technically is able to calculate durations, you should pre-compute them because it's just a lot easier if you just say, okay, this is the number of dates in between something.
Yeah, I think he also mentioned that some of these variables are actually something that you would only find if you introspect your data set. So he said that there are certain stores in the Rossmann inventory that are open on Sundays and some that are not. And because of the ones that are open on Sunday, they have a non-zero variable for sales, and those stores did actually quite a lot of sales on Sundays compared to others. But if you just regress to the mean, then you would have washed all that data away, right? So you have to be careful with that. So shall we look through this paper a little bit? So this one is looking at taking entity embeddings. It reduces memory usage, speeds up neural networks compared to one-hot encoding, but more importantly, by mapping similar values close to each other in an embedding space, it reveals intrinsic properties of the category of covariables. So I haven't read this paper either, but we can look at this a little bit.
Is there, I know we talked about embeddings quite a lot, and it's late to ask this question, but is there any theoretical justifications for why embeddings work so well, or is it more like a philosophical one? No?
I think
Empirical.
Yeah, empirical philosophy. I mean, there's always you can interpret it like king minus man plus mean minus woman.
So
this is what I say is philosophical.
No, it's not philosophical.
Yeah.
So what happens is that in NLP there is this idea of distribution similarity, right? So people have been trying to capture distribution similarity. Distribution similarity means a word is known by the words with which it occurs. Okay? You always try to model a word because there is a certain statistical distribution by which language is generated and occurs in human languages, right? So in the past, the distribution similarity has never captured the notion of distances between words very well, right? So even if you take things like word nets, where they try to capture how far away one word is from the other by means of hierarchical distances, where words are arranged into sets. It's basically word net is basically a semantic net, right? Even that doesn't give you this. It doesn't project. If you take say TF-ID of vectors or some other representation of those words, it doesn't translate into distances in the dimension in which the words are expressed. Right? Basically, if you add or subtract those two words, the output of that does not mean anything. Right? At best, even if you take cosine similarity, it tells you the distance between these two words with respect to those two words. I mean, there is no global picture, right? Word embeddings gives you a global picture. It says that this is the bigger space. This is all that's, and in this space, each word occupies this particular point, and that's the specialty of word. That's why it works so well. And secondly, it is also dense. It is also a dense representation of words. So
that's actually a point which he two sentences Jeremy mentioned was basically there was a question if you should ever choose the dimension of your embedding larger than the dimension you would get when you have one hot encoding. So basically, you have more dimensions than you have categories, which would not be dense, right?
No, wait. Categories and these are okay. So one hot embedding of a word is equal to the vocabulary you have.
Yeah, okay. Sorry.
So I think Jeremy was referring to something like dates of the week, right?
Yeah, you have 7 days
So you have
of the
7
week,
days
but
a
you
week.
have a 10-dimensional embedding.
For each date.
Yeah, for each.
So why is the categorical output related to your dimension?
No,
I
I
mean,
think that the question was, does it ever make sense to have embedding size larger than the discrete amount of categorical variables, right? So if I only have 7 days, why would it make sense to make a 50-dimensional embedding for a date, right?
Yeah, now it means what your embedding means. That's in words, it's a different matter. The embedding represents its position in the semantic space. The categorical output that is utilizing this word representation may not have a direct relation to the embedding at all, right? You understand what I'm saying?
But
It's always the case.
If I have only 7 points,
In a
that's
different space.
But
In
I
the
mean,
one
I
hot
have a
space.
network after that. The network can deal with my how it's mapped in other spaces.
Right.
I only have 7 points. Like even if they lie in an impossible thing in this high space, they will always only lie in a 6-dimensional space, right? So why would I put them in a 10-dimensional space?
No, the dimension, the word vector level dimensions at your bottom layer is trying to capture the semantic space. It is not in the space in which you're doing the categorization. Okay. The semantic space makes sense because you are trying to capture the word in the context in which it appears.
So Muthu, you're talking about words, but we're not talking about words. We're talking about we're talking about variables that take on discrete values that are with probably a small number of values, right? So if you take day of week, it only has 7 values. Would it make sense to take that type of categorical variables that only has values 0 through 6 and map it to an embedding space where I have more than 7 integers 7 floating point numbers to represent it? That is the question, right?
Okay.
So here there's a little bit of paragraph about this, right? Okay. So this particular paragraph here says, okay, I have the bound for the size of the embedding should be between 1 and m-1, where mi is the number of values for the category of variable x.
Here,
right?
Here the way they are treating embeddings, it's similar to the way you do encoding of data in standard data mining, right? If you have 7 variables, 7 outputs for a particular variable, you usually take 7 bits and
that's what.
Yeah.
But then usually if there is some other context that you want in the embedding.
All I'm saying from a mathematical point of view, it's impossible that, like, even if, let's say you have a 20-dimensional space which actually represents the semantics, your 7 points will always lie in a 6-dimensional subspace of your 20-dimensional space. And you don't care about the 20 dimensions if all your points lie in a 6-dimensional subspace.
Agreed.
Yeah. And the weird thing is Jeremy said that sometimes it helps to have a higher dimensional space.
I think the important part is that when you move to an embedding, you have much more fine-grained detail about how close 2 values are to each other, right? So, for example, Sunday and Saturday should probably be closer in the space than Friday to Saturday, because that's one's a weekday and one's a day. In one hot encoding, you wouldn't get that at all, right? So it depends on how rich your data is. I think it's actually not a matter of how many categorical values there are, but how rich your data is in order to find out what the nuances of the similarity is. So I think the dimensionality of the embeddings would actually be more determined on the quantity and the quality of the data set.
That's
rather
always
than
the case, yeah.
rather than anything else. Yeah.
Right. it's always a trade-off between the dimension of you choose is always a trade-off. It is a cursor dimension problem, right? You have enough data to for covering.
Like okay, not in this talk, but in an early, like in the
another
first part, he
topic.
mentioned this heuristic. You should use like if you have wait, let me get the words right. What's M standing for? The number of features.
The number of values that the category can get.
You should always choose, like his heuristic is choose half the number of values, but never more than 50. That's his heuristic, and he said that works very well. So that only depends on the number of values, not at all on the size of your data set.
Yeah, I think that's a heuristic. It probably works okay. I don't think it's mathematically sound, but I think it's okay. I think the important thing is you have enough dimensions to be able to represent nuances of similarity in your data, right? I mean, even with word vectors, which are much more principally built because they're using contextual information to start the embedding process, right? They initialize it there. You know, even if you have 150 or 300, those are humongous reductions from the original one hot encoding of 30 or 50 or even 100,000 dimensions, right? But you don't actually get that much change in it, right? Because the amount of fidelity that's not there in the 50-dimensional space that's there in the 100 is actually not that much more. I think there's a lot to be said. Just moving into an embedding space of maybe even 5 dimensions is probably okay for categorical variables with less than, let's say, 50 values, right? In the case with words, you have 100,000 possible values for a word, so probably you need a couple more dimensions than just 10, right? So what he said is like take the number of things like he said like if day of the week has 7 values, you take anywhere between 3 to 50, right, to make that dimensional embedding, right? So they I think they do have something more to say, and I haven't read any of this.
Like they just
Sorry, go ahead.
No. At one of the papers you were talking about, you were saying, okay, they just choose 10 as the embedding space dimension for everything.
Yeah, and that probably works okay too.
Yeah.
For exactly the same reason that even in 10 dimensions, you're getting fairly fine-grained information about where things can go and the similarity values that you can get, unless there's like a huge number of possible values, like in the case of words, right?
Yeah.
For normal categorical things, it's probably okay.
Is there another, like except for computation purposes, is there another reason to reduce the space, the dimension? Of course, it makes the computation.
No, it's not just about computation.
So reduction gives you 2 things, right? It gives you more dense data, right? So you do dimensionality reduction, your matrix goes from sparse to dense. That's a very important part.
But also just helping you with computation.
It also helps with computation, right? Because then you have a small matrix to do computations over.
Yeah.
So it has those 2 benefits, but you also want to make sure you don't lose fidelity in your data. Right?
So that's why that's basically the lower bound is you don't want the fidelity, and the upper bound is mostly computational.
Mostly computational, but also that coverage. Yeah.
Is key.
Yeah, that if you have a sparse matrix, then you're not going to get very good measurements, right? You want your matrix to be fairly dense, right?
No, I'm a bit, but okay, good. I have to think about it.
Okay, so when you do dimensionality reduction, you're basically taking all the 0 values in the original matrix and throwing them away and putting non-zero values that might be minuscule but have some signal, right? So that's
having 0, like having only 0 is different from
yeah. So I mean, typically you do something like PCA, right?
Yeah.
And then you'd throw away a lot of dimensions, and then you're getting a fairly
signals.
Yeah.
That's what you want.
You get a dense matrix with a much smaller rank that can approximate almost 100% of your signal anyways, right? You think about, graphics encoding that's lossy like JPEG, you can throw away, I don't know, so many of the components and you still get a picture that looks pretty close to the original, even though you've gotten rid of 80 to 90% of the data. Yeah, so I think that is more of the value of doing embeddings for that reason. So basically, Jeremy, I think is saying that take whatever you want that is categorical variable, and then throw it into an embedding space, and then let the gradient descent optimize the values for those dimensions, right? Where you have determined the number of dimensions, probably based on something like PC at the beginning, or you can just set it to 10. I don't think it matters that much, right? Again, it's going to be a function of how many values that categorical value can take on, and then how many data points do you have to measure those categorical, not the categorical values themselves, but the relation between the categorical values and the label that you're trying to induce, right? So that it can be fine-tuned.
And that, like, on the one experiment, like where I used that, like I played around with the dimensions, and like except cutting it too low, you didn't have like much influence. Like it was more or less noise if you had 25 or 50.
Yeah,
more or less the same.
So I think that's something important, right? They did say some things about looking at certain parts of the data and trying to engineer good features for that, right? So what was this that they say? German state each store belongs to. So that helps because you're getting locality information about where states where stores might have similar behavior if they're in a similar area, and then whether what did they say? Weather data, right? So if it's raining outside, perhaps not that many people are going to go to the store, or if there's a football match, probably people are not going to go to the store.
I wanted to say even sports events, like if you have been in Germany during the World Cup, especially during the final, the streets were completely empty. You've never seen the streets in Germany so empty because everybody was at home watching the game.
Right.
And like 2 hours later, after we had won, you've seldomly seen the streets so full because everybody was outside. So even sports events, it's like a little understating the event.
That's actually quite important, right? Yeah.
On the German.
Yeah. So I think there's these types of variables that are present in a lot of data sets, and if you're not a data scientist and you don't look closely at it, you just think everything is the same. And it's probably true of the pediatrics data set that we saw earlier, right? But the important thing here is when you observe that type of data, you want to apply an analysis where the algorithm can learn the importance rather than you a priori give some importance. I think that's the problem with the PIM and the PRISM metrics that we saw in the other paper, as they're hand engineered, so they're hand tuned. Whereas that particular paper that we were looking at earlier, the pediatrics one, didn't have a really good method for dealing with that information. I think there's probably quite a lot of optimization even in the neural network architecture that they had there.
Another like more you put the effort in getting the features right, which have high importance, and you don't spend like too much effort in fixing features which don't matter at all.
Yeah, I think that's very true. You can use that as a first pass pruning of the data, and as the other taxi prediction paper said, right? You basically can throw away a lot of data, and it won't hurt you as long as you are not throwing away the key data points and trying to do, as you said, more with the data that actually matters, right? And use that appropriately. So that's exactly what they did in that paper, right? They said, okay, the last 5 destinations are pretty important. And when I deal with those destinations, I want to cluster their information together so I can get a more accurate prediction of landmarks that people go to, right? So I don't think we wanted to actually take a look much at the methods here. T-SNE. Okay, well, we can come back to this if we want. The other paper was the tiramisu paper. Do we want to talk about this? It's based on DenseNet. We talked about DenseNet last week a little bit, right? So this is a ResNet, but the ResNet has, instead of residual encodings only going through certain branches, they're feeding in all of the input, right? And that makes a block, and you have multiple of these blocks in the data set. So in the architecture. Do we want to talk about DenseNets in more detail?
Sure.
Okay. So
they generate these that are useful for many things. It's useful to know about these breakthroughs.
Right. So we talked about residual nets and highway networks before, right? The ideas behind this is that, okay, when you have a very deep architecture, you're losing information about the gradient. So you have to reintroduce that information at the right time so that the network can still converge. Otherwise, you have this problem where the learning rate is not set appropriately for deeper layers, and basically you're not moving the weights a lot, right? So the residual and highway network does this, but the DenseNet is doing this. For example, here, right, you're getting information not just from the previous layer, but from all the previous dense blocks and feeding it in, right? So that's the idea of this part. So we can read this a little bit. Figure 1 illustrates this layout schematically, right? Crucially, in contrast to ResNets, we never combine features. Instead, we combine them by concatenating them, not adding them together. So at each level, we're getting more and more input. Okay, it represents different thing. It represents feedback from, you know, the layer, the dense block before, the block before that, or the block before that one, right? So that means the ELF layer has L inputs consisting of the feature maps from all the preceding convolutional blocks. Its own feature maps are then passed on to all L minus L subsequent layers. And so you get something very thick towards the end. And that's why they call it a dense net. So I think what they mean by this is that the feature maps that you're introducing at each layer is getting additional information rather than re-engineering the feature map that was at the previous layer, because you're pretty much passing the previous feature map down. So at each level, you're inheriting all of the previous work that was done, plus you're adding a couple more pieces of work, and therefore you don't have to redo that, and that means that you don't need additional parameters to redo all of the lost work that you threw away in the previous ones. All right, so they write something more here, right? Recent variations of ResNets show that many layers contribute very little, and in fact can be randomly dropped during training, right? But that's what they're trying to do away with. They said, don't bother dropping it, just pass it on. You know, you don't have to drop it and re-engineer it. You just keep it along, and then just propagate a few more parameters for the new feature maps that are being generated at that level. All right, so our proposed DenseNet architecture explicitly differentiates between information that's added to the network and information that's preserved by pushing it downward, adding only a small set of feature maps to the collective knowledge. That's what we were saying, right? And keeping the remaining feature maps unchanged, and therefore the parameters don't need to be re-instantiated. And the final classifier makes a decision based on all feature maps in the network, right? So it means that at this level, we have a large number of feature maps at the beginning, then I add a couple more, and then I add a couple more, and towards the end I'm adding very few, because I already have this very large inventory of all of the feature maps that come from the previous blocks.
Are there pooling layers in the blocks or between the blocks?
So let's see, what do you have here?
They have batch normalization.
Yeah, I don't know. I don't think
They don't
have pooling. Yeah,
so
I don't think
the
they're trying to reduce anything. I
Right.
think they're just trying to continually augment rather than
In
reduce.
the end, they have to.
Yeah.
Is it only in the output layer, or is there one point where they get out?
Radhika, you were saying? Did you say something?
Yeah, they describe the architecture in section 3.
Section 3.
So,
Yeah, dense block.
So each of the things in figure 1 was a dense block. So they do the pooling after each dense block.
Yeah,
so you have a couple of these stuck together.
Dense block is basically a fancy RESTnet.
It is a ResNet, but just trying to fix parts of the ResNet architecture, right? So the ResNet was trying to fix specifically that the gradient was disappearing, right? So they fixed that, but then they lost computation, right? Because they were throwing away things and redoing them. Right. So the dense network is just saying, why did you throw away all of that? You can actually keep it around. So the idea behind that is just like we said here, you keep around all these computations, you pass it down to the next level, you add a few more computations, these green ones to the red ones, right? And then when you go to the purple layer, because you've already done the batch normalization and the nonlinearity, you preserve all that you've previously done, and you just add a couple more. So this is the dense block. Right, 5-layer dense block. Right, so it's 5 layers, but you have many, obviously many filters at each layer. Right. So that was this one. All right. Is there anything more we want to say about that? I don't think so. I think the important part here is what they said earlier, is that when they're getting information at each area, they are not summing them, right? They're concatenating them. So this is a key point, that they're not losing resolution, right? They're just keeping everything and then saying, to heck with it, I'm just going to add more and more stuff. And then at some point they say, okay, we've done enough computation, let's go lose it, right, through pooling. Okay. So they tell you a little bit about the growth rate. We've already talked about that, because computation cost, when you keep on concatenating things, is going to get out of hand. So I guess that's why instead of having one huge dense block all the way through the network, you have this pooling collapse things, and then you do it all over again. So that's their entire architecture. All the dense blocks are the same. No, they're not all the same. They have different number of filters as they go down.
Those are tunable. You can experiment on. Since you have pooling layers between each of them, then it's also obvious.
Right.
Your output size for each of the blocks would be different. There's no point in doing pooling. Right.
So this gives a good segue to the tiramisu paper, because they did it exactly the other way. They have it going down and then coming back up on the other side.
So it's like a bidirectional system.
So I don't know. Do we want to go to that screenshot of the whiteboard that Jeremy showed us in the video? That one was pretty helpful, right? Let's see. I don't know how to get there. Yeah. I'm trying to find that one tiramisu. Yeah, because it looks like the dense net, but it has another thing, another column going up the other side, right?
And it looks like it has
Is
less
it in this?
connections in total, because you're not always feeding everything. You just at certain point feed. Let's just look at that one.
Yeah, because it's here too, except it's not in the graphical form, right? That is the whole thing there. Where is it? It's towards the end of the paper.
Yeah.
You want to turn on audio for this?
The model knows pretty much, this is a tree, and this is a person, and this is a house, and it just needs to get the fine little details. A few days ago, I actually drew this on our whiteboard when we were explaining it to Melissa, and so he's shown us every stage here. We start out with a 224 by 224. This is what Brendan thinks the tiramisu looks like, just by the way. 224 by 224 input, goes through the convolutions with 48 filters, goes through our dense block, adds another 80 filters. It then goes through our, they call it a transition down, so basically a max pooling. So it's now size 112, right? We keep doing that. Dense block, transition down, so it's now 56 by 56.
So this part is pretty much the dense net paper that we just saw, right? Because every time they go through this dense block, it's the same thing, right? And then they're doing the pooling and convolution to do the step down size for the image, right? And then they're redoing it.
28 by 28, 14 by 14, 7 by 7, and then on the way up again, we go transition up, it's now 14 by 14. We copy across the results of the 14 by 14 from the transition down and concatenate together. Then we do a dense block, transition up, it's now 28 by 28, so we copy across our 28 by 28 from the transition down, and so forth. So by the time we get all the way back up here, we're actually copying across something that was originally of size 224 by 224. It hadn't had much done to it, right? It had only been through one convolutional layer and one dense block, right? So it hadn't really got much rich computation being done. But the thing is, by the time it gets back up, all the way up here, the model knows pretty much, this is a tree, and this is a person, and this is a house, and it just needs to get the fine little details. Where exactly does this leaf finish? Where exactly does the person's hat finish?
Right, so I guess what he's saying is that most of the computation here is just to get some like coarse grain results, right? And that the bulk of the computation is actually just going through this part here, right? Because
what does TU do?
Transition up. Let's go to the paper.
Decon layer.
See. Oh, what happened to my other window? This is our TU. So transition up. Let's take a look at what that does. Sorry, go ahead.
Go down.
Go down.
There. We didn't use
Transpose convolution stride.
transpose. Isn't that another word for the opposite of a convolution? Transpose convolution? Like,
Yeah.
what's a transpose convolution? I think it's one of the many words for deconvolution.
That's what I thought. I mean, that's the only way to.
Yeah.
And then they say
So it's a deconvolution layer. Okay, got it.
Yeah, then they say don't say deconvolution.
Yeah.
Why?
Because deconvolution is the opposite of convolution, but we actually don't do convolution in a convolutional neural network.
Yeah.
We do cross correlation, right?
Right.
Yeah. So I think it's just.
Even use convolution.
So yeah, now everything makes sense. Okay. So normally when you are doing
It's the opposite of what we normally do in the convolutional neural network, which is not convolution. Right?
Yeah.
So that's what.
So when you want to do deconvolution in normal convolution networks, the place where you actually can't do decon is max pool. When you have max pooling, you can't decon. Okay, so this is a problem. This is why he is taking the input from the other side and concatenating. And
Exactly, because you can't do you can't undo a pooling off.
You can't do pooling, exactly.
Right. So when you have these cross connections, then basically you are getting the exact image of the right size, and you are already getting the results from the more coarse-grained image recognizer.
And like
So you just do it at multiple levels. That's all.
So the first layer is usually like for recognizing shapes, right?
Mm-hmm.
Like if you think about them like that, and that's exactly what the information you want. You know, okay, this area is something. I just want to like have the shapes of this area, and that's what you get back from the first couple of layers.
Right, right. So each worker, as it is, if I'm sitting here in this pipeline, right, I'm getting rough results from my friend who's lower down in the tiramisu, that there is a certain like strawberry here, there's a piece of chocolate flake there in the tiramisu, and I need to localize it, right? I need to say exactly where I think it is in my version of the image, right? And in turn, my version of the image is being passed to the next person in line, who has a much bigger, higher resolution image, and they're going to do the same process.
Somewhat like a autoencoder or VA kind of an idea.
Yeah.
Right?
Yeah.
Yeah.
Because you're basically, this is your entire bottleneck, right? You're doing this at multiple resolutions, but the key interesting point is, as you just pointed out, you can undo max pooling, so you just get it from the previous part, right? You're just like, I pass you. I get the image that you were going to throw away when you get down there. I just can preserve it and send it over.
But this is less dense than the dense net, right? The dense net basically has these arrows everywhere.
No, you
But
still have a dense net. The dense part is in each of these dense blocks. So this particular dB here is equivalent to that figure 1 in the previous paper.
Okay, so this is okay. So you have lots of dense.
Yeah, each of those is dense blocks. Yeah, so it's no less dense. It's just layered.
No, what I mean, you don't like this is a dense net.
This
is not. So you don't have all the connections from here to there.
No,
Otherwise,
no.
you wouldn't never downsample it. You just
Right.
have like
even in that paper,
60
we do the same thing, right? So if we go back to that, yeah, okay. Here, this is a dense block. It's the same dB block that you saw here. Okay,
Yeah.
This entire architecture, this thing going down is, I think, equivalent to this, right? It's just that this is written across, right? So here's our dense block 1, here's our dense block 2. In the middle, we have what they call transition down in the other paper. So this is a dense block 1, transition down, dense block 2, transition down, dense block 3, transition down. Instead of doing the prediction, of course, I now have a very small image. I do the predictions. Then I take this entire architecture and do it in reverse to go back up, right? So yeah, so it's just zoop, right? It's like the UNet or whatever you want to call it. I think he makes some references to those papers as well. Okay, so we are out of time, so I guess that's it for today. Yeah. Okay, so that's it for our course. Thanks for coming, and I wish you the best in your career at SOC, and I hope that we'll see you again for your talks, and even next semester, if you want to come back to this course, we'll be running another version of it. Okay? Yeah. Thank you.
Thank you.